Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of startups and the funding given to startups in India. And we have a bunch of features about the startup and then the amount in US dollars that the startup is given. So let's hop into the notebook. We're going to be using NumPy and Pandas for working with the data. And today what we're going to try to do is learn how to incorporate a Keras model into an scikit-learn pipeline. So for this, we will need, we're going to use the train test split function to pre-process the data. And then for our pipeline, we're going to use the one-hot encoder, standard scaler, column transformer, and then the actual pipeline object itself. And we'll build a model with TensorFlow. And we'll just use R squared score from scikit-learn to analyze the results. So let's hop into the loading up the data using pandas.read CSV. We can grab the file path up here to the CSV file. I'll copy that over, paste it in, and we can take a look. Alright, so we are going to have to pre-process this data quite a bit. We have some steps to perform. Let's look at data.info to see if we have missing values. And yeah, it looks like we do have some missing values in most of the columns. A lot of them actually in remarks. Alright, so let's go ahead and we're going to make a function called pre-process inputs. And this is going to take in a data frame. And right now all it will do is make a copy of the data frame and return that copy. So what I'm going to do is store the processed version in X, pass in data, and then right now X will be just a copy, but it will be the copy that we perform the pre-processing on. So the first thing I want to do is drop some columns that we're not going to need. So the one column I know we won't need is the ID column at the beginning. So let's I'll just say df equals df.drop, and from axis 1, which is the column axis. Now, for the other ones, we want to drop high cardinality columns. So what I mean is, we have a bunch of categoricals. These are our categorical columns. And if one of them has too many unique values, it can be for one, as the number of unique values approaches the number of rows we have, the feature becomes less and less useful because there is less and less of a way to create similarities between training examples. On the other hand, it also will slow down our model substantially if we try to one-hot encode a high cardinality column, because what you end up with is like 1,000 new columns, which can really, one, it can lead to overfitting, and two, it will just take a long time to train. So what we can do here is get a dictionary that's going to map a column name to the number of unique values in the column. So I'll do x sub column.unique and take the length, and do that for every column. We could just do x.columns. We'll just have to remember to exclude the non-categorical values. So these are the categoricals. Remarks you could consider as categorical, but I think we're just going to drop that column because it has so many missing values. So just looking at these, it looks like 2 of them are standing out to be high. 3 of them actually are high cardinality. The investor's name, subvertical, and startup name. This one is sort of pushing it, but I'll keep it on. 822 new columns is what we'll end up with. So let's drop these. This one is really high, so there are some duplicate names in here. But overall, there's not a lot of useful information in this startup name column if we're trying to predict the amount. Because you know the name isn't really going to be a huge contributing factor. So let's drop startup name, subvertical, and the last one is investor's name. But all the rest should be valid features to use. So I'll say drop ID and high cardinality columns. Alright, this is the remaining data. Now let's look at the missing values. So x.isNA will give us a true wherever there's a missing value. We can then sum over the rows to get the number of missing values in each row. So everything except the date column has missing values here. However, it'd be more useful to know the percent of missing values in the column, so we can do that by getting the mean instead of the sum. And in general, you usually want to drop columns that have more than 25% missing values. But what's important to note first is that our target column has missing values. So the target column needs to be taken care of before any of the features are dealt with, because we can't be predicting on missing values. We can't fill the values and then predict on those. It doesn't really make sense. It would be improperly labeled data. So let's go and drop any rows that have missing values in the target column. So drop missing target rows. So how do we get these? Let's just take the name of the column and look at the column, and then use the isNA function just on this column. This will give us our true-false array, whose length is the same as the number of examples we have. We could then use this array as an indexer for x. So this will give us back just the rows where we have missing values in the target column. We can then get the indices for this by typing .index on the end, and then we'll drop these indices. So up here, excuse me, we can say missing target rows equals these indices. I just have to replace x with df, and then we'll drop those indices. So df equals df.drop missing target rows from axis 1. And this, actually, sorry, from axis 0, since these are rows. And we want to reset the index afterwards, since we won't have consecutive indices if we drop rows. Drop equals true just ensures that the old indices don't become a new column. Alright, so now if we look at our isNA, we should have a 0 for the amount. Alright, there we go. So no more missing values for the amount. And the remaining missing values are all fairly reasonable. The only one that's not is remarks. This has 83% missing values, and we're probably just going to drop this column. You can't fill in 83% of the values, or you actually get pretty bad performance from the column. So let's drop columns with more than 25% missing values. That's actually just one column, which is remarks, and dropping from axis 1. Alright, so now the remaining missing values are quite easy to deal with. I guess we can just fill them in, and you'll notice that the only 3 columns with missing values are our categorical columns, and they're nominal as well, which means there's no ordering between the values. So when we have nominal features like this, we're just going to fill the missing values with the most frequent occurrence. I mean, that's the most basic way you can do it. So let's fill categorical missing values with most frequent occurrence. So we can do that with the mode. So for each column in, and we're going to list out the 3 categoricals here. So for each of these 3 columns, we're going to take the column and call fill_na on the column. Fill_na allows us to fill the missing values with whatever we pass in here. So let's pass in the mode of the column. And the mode function actually returns a pandas series because it could have multiple modes. So we take the first mode with sub 0. And then let's set that equal to the original column, or set the original column equal to this new filled version of it, and take a look. We have an issue. City location. Oh yeah, so actually, if we look at x.columns here, see city location actually has 2 spaces in the middle, and for some reason when it displays it on the data frame, it only shows 1 space. So you actually have to make sure that you're paying attention to the actual, I mean, I assume it was improperly entered. Alright, so here's x now. And if we look at the missing values, we have no more missing values. Just to double check, we sum over both axes to get the total number in the whole data frame, and that's 0. So we're done with missing values. Now we can start working with encoding. So we're going to use pipeline today. So our categorical variables can stay the way they are, but the date column we should probably encode. So let's do this. Let's take the date column, which is this long name here, and we want a way to pull out the year, month, and day. And you'll notice it's in day, month, year form. Let's take, let's use the pandas.toDateTime function to convert the column to a datetime column. We're actually getting an issue. If we look down Y, you can see there's a value here with a typo. There should be a slash in between the 07 and the 2018. So what we'll do is clean up the column first. Clean date column. And we can do that with the replace function. Take the column name, set it equal to itself with replace called. We pass in a dictionary to perform our mapping for values in the column. And so any typos we can correct here. So we want to correct this one. And these are strings. So if we ever find a string that looks like this, just correct it to the same thing but with a slash in there. Now we run this and take a look. So we got our x back, and now we look at we try to convert it to datetime again. We have another one. So out of bounds nanosecond timestamp. So this one's not as we're not actually sure what's going on here because you can see we have a valid date. So I'm not sure exactly why we're getting this error, but it's pretty obvious that we have some problems in the dataset. So what I'm going to do is instead I'm going to pass in here errors equals coerce. So by default this is errors equals raise. That will raise an error when we get a problem. You can also do errors equals ignore. That will just convert what it can and leave anything else. We're going to do errors equals coerce, which will turn values that it can't that are not valid into not a time objects. So those count as missing values. And you can see if we sum over the missing values here, there's 3 values in here that it was unable to convert. So let's take a look at what those are. So it's hard to see here, but we can do what we could do. Look at x. We can put these together. So we can concatenate pandas.concat the x and then this new datetime column that we created using a column in x. And we're concatenating on axis 1, which is column-wise. And you can see we now have this and this. So the reason I'm doing this is now we can take the, if we just take the is and a of this, we take this dot is and a. Oh, I forgot the errors part. We can use this as an indexer for x. I guess I should have just done it this way. Okay, so using this, what we did here is we get the, let's just delete this. We get the missing values for the this datetime column, which essentially is the ones that we could not convert. We use this true-false Boolean array as an indexer for our original x. Now we can see the examples that have the issue. So there's 3 issues here. The first one is this, which is we forgot a 2 for the 2015. So let's go in here and just add that in. This is going to get converted to the same thing, but with 2015. Then we have this one, which is a little more complicated, so let's just come back to that. And then the last one here, which has 2 slashes instead of 1. So just remove one of the slashes. Now if I run this, we take a look, we should only get 1. So this is our single example that is problematic. And you can see it's actually a problem not just with the date column, but there's other ones in here that have the same strange prefix here. So I actually found there's actually quite a few examples in the data frame that have this prefix on their entries. So what we're going to do is do an element-wise map across the whole data frame to try to remove this prefix wherever we see it. So let's do that before we drop the missing target rows. Let's say clean these weird examples. So we can do this with apply map. Apply map will apply a function to every element in the data frame element-wise instead of column-wise. The map we want to apply is a lambda function that maps every x to x.replace, where we replace any time we see that with the empty string. So we're just deleting it. And we only want to do this if we're dealing with a string. So if the type of x is string, and if it's not a string, we'll just leave it as it is. We won't even check. All right, and now we go back here. We still have an issue. It looks like maybe did we do something wrong here? Let me look at it this way. Let's try applying the same map to x. So x.apply map. I'll just type. This is a bit weird. All right, I'll try. This is getting complicated. Let's take this. Well, I'll figure this out. I don't want to waste time. Oh, I see the issue. Yeah, the problem is we have backslashes in the replace string, and these backslashes will actually be treated as escape characters or escape flags. So we want to make sure it's a raw string, so we'll put the R there, and that should work. Now if we look at this, we have no more rows with problems. All right, so we've cleaned up the date column, and we've also cleaned up these issues. So now that we've cleaned up the date column, let's actually convert the column into a datetime object and then extract the features. So extract date features. We can take, let's just take the name of the date column and set it equal to itself with the pandas.toDatetime function called on it. And we don't have to pass in errors because we know there's no more errors. So right now it's a datetime object. What's nice about datetime objects is that let's apply a function to this. Let's say we wanted to take the year. If this was a string column, we could do that by saying x, take the first 4 values of x. But what's nice about datetime columns, we can actually just do x.year. So for a given datetime object, we get the year from the datetime object. That should return it properly. So let's do this up here. What we'll do, just whoops. All right, we'll replace x with df, and we're going to take the years taken from the datetime column and set that to a new column, which we'll call year. We'll copy this over once for month and once for day. So this is the month column, and that comes from x.month being applied to each date. And this is the day column that comes from x.day being applied to each date. Then the last thing to do is drop the original column from which we created the dates. So that would be this one. And we're dropping from axis 1. Alright, here it is. So year, month, and day now have their own columns. We don't have to worry about that anymore. Alright, so I think the last thing to do is to deal with this target column. So it actually has some issues in there. There's commas right now. I want to remove the commas and just delete them, and then convert the whole column into a float column. So let's try this. I'm going to do that up here. I guess right after we remove these examples. We'll say clean target column. And we're going to take the column, which is amount in USD, and we're going to set it equal to itself with the replace function called. Actually, no, we want to apply a function. So for every x in the label column, which is one of these things, so x looks like one of this, all we have to do is take x.replace, replacing any comma with empty string. Float has no. Okay, so interesting. So there are some floats in here, which is very strange. We know there's no missing values, so I'm not sure why there's floats. Let's first convert it to a string column, so as type string, and then try. Alright, so that works. And we do have some missing values here. Why do we have a missing value? Oh yeah, we did. I thought we dropped them. Oh, I see. We did this before we dropped the missing values. Okay, so instead of converting it to string, what I'll do is just if x is not a missing value, so string of x does not equal nan, and if it is a missing value, we'll keep it the same way it is. Alright, that should work. There we go. Okay, so now that we've converted it, now that we've removed the commas, we're going to try to convert the column to a float column. So we'll do that down here. Convert target column to float. So let's take the column and type dot as type numpy dot float, and let's just do this for the whole column. And we got an issue. Alright, so it looks like there's some other values in here that are not proper prices. So we've removed the commas, but there are some other values we need to worry about now. So what I'll do, we can make a little loop here. We can take the amount column and we can iterate through all the items using iter items. So for every iter items will return an index and then that item for a given series. So for I and x in the iter items of amount, we'll print out the x. Actually, what we'll do is we'll try the try catch block. We'll try setting x to be a float, and if it doesn't work, except we'll print out x. So this will give us, we'll print out all the problematic examples. So let's do this. Let's make a copy so that we're not modifying the original. We'll call it z and z.iteritems. So dot copy. Alright, and here are the problematic examples. Alright, so it looks like there's 4 problems. Undisclosed, unknown, undisclosed with a capital U, and then NA. And then there's this one that's numeric. We just have to take the plus off the end. So let's just copy this and go up here. And we're cleaning the target column. I'm going to paste that in just so we can see what we... I should have copied this. Paste that in so we can see what we're working with. And we'll do a replace. So df sub amount in USD equals the same thing, dot replace, and then here we can provide the mapping to replace things. So let's replace undisclosed with a missing value, numpy.nan, unknown with a missing value, numpy.nan, undisclosed with a capital U with a missing value, and n/a with a missing value. And then the last thing is this thing. We don't want to replace it with a missing value. Instead, what we'll do is just replace it with itself minus the plus. Alright, let's see if this works. So there's our x. If we look this now, we have no more problems. Delete that. And you can see it has been converted into a float. So we have no missing values in the whole data frame. You'll notice also that I did the cleaning before I dropped missing target rows. So all those missing values were taken care of by our drop. So we have no more missing values. We have numeric data in our target. These are numeric. Then the remaining values are our categorical values. So now we can build our pipeline. So the last thing I want to do in the pre-processing function is split our data. So split df into x and y. First we'll do this vertical split where y is just the target column. That will be amount in USD. And then x is all the rest of the data, so we're dropping that same column from axis 1. Then we'll do our horizontal split or train test split. This will create 4 new sets of the data. And we'll use the train test split function from scikit-learn, pass in x and y. We'll give it a train size of 70%, keep shuffle equals true, and give it a random state so the shuffle is always done in the same way. And we'll return these 4 sets of data. Get them back over here, and we'll take a look at xtrain. So this should no longer have the amount column, and it's just 70% of the data. Then ytrain is just the amount column, and the indices match up. Alright, so now we'll build our pipeline. So we are trying to train a Keras model and embed it in a scikit-learn pipeline. So if we're going to do this, we're going to use tf.keras.wrappers.scikit-learn.keras regressor. And this is actually like turns a Keras model into an sklearn type model. So this thing, we have to pass in a function that returns a compiled Keras model, and it will take the compiled model and turn it into a scikit-learn type model. So let's create the function to build it. Call this build model. And here we just create like a proper Keras model. So we'll have inputs. That'll be our input. Now I should point out the shape of our input. It's actually going to be the shape of the data after it's been one-hot encoded. So that's going to change. So we're going to leave this blank for now. But this is going to have 2 hidden layers. So dense layers, let's give them 128 neurons and a ReLU activation function. Pass in inputs here and duplicate and pass in x to the second one. Then our outputs will be a dense layer as well. Since this is a regression task, we're only going to return 1 value with a linear activation, which means no activation. We want this 1 value to take any value it wants. We pass in x, and then we'll create the model, which will be tf.keras.model. The inputs are given, and so are the outputs. Then we'll compile the model and return it. So we're going to compile using an Atom optimizer. For loss, we'll use MSE, mean squared error, since it's regression, and we'll return the model. So this is the function we need. Now I'm not going to run it yet because we still have to put the shape in. But what we could do is then pass in build model as the function for our Keras regressor, and that would turn the model into a Keras regressor. Alright, so now let's build the rest of our pipeline. So we'll start off with a one-hot encoder. So this will be our nominal transformer. And this is a sub-pipeline. So we create a pipeline with the steps being only one-hot encoder. I'll give it the name one-hot and one-hot encoder, turning sparse equals false so that we don't return a sparse output. And then we're going to pass the nominal transformer into a column transformer so we can tell the pipeline which columns to apply this one-hot encoding to. So column transformer, these are all sklearn objects. And then we pass in the transformers we're using. In this case it's just one, which is our nominal transformer, and that comes from nominal transformer. Then we pass in the columns that we want to apply it to, and that's just these 3 here. Remember there's an extra space there, so I'm going to have to make sure to add that. So in here, just clean it up, add that extra space, and there we go. So I also should point out we need to include remainder equals pass through. So this says all the columns that aren't being touched by the column transformer, just leave them be. Don't drop them. Alright, and let's call this preprocessor. Alright, then we'll create the actual pipeline. Actually, let's create the regressor. So that comes from this. So the Keras regressor, we'll call that one Regressor. And then we'll create the whole model. That's going to be our final pipeline. The steps here, first we have our preprocessor, which we already created. Then we're going to scale. So our scaler will be a standard scaler, which will give each column a mean of 0 and variance of 1. And then our final regressor comes from this Keras regressor we have here. Alright, there's our model. Now, before we continue, I want to know the shape to pass into this function. So what we can do is just remove these two parts from the pipeline. So we're just using the preprocessor. And the output of this should have the proper shape. So if we fit this model, and because the last transformer in this model is a one-hot encoder, we can use fit transform to get back the data. So we'll fit transform xtrain, and then take the shape of this, and you see we have 532 inputs. So those inputs will be scaled, and then they'll be sent into the regressor. So 532 is what we want to put up here. The model takes in a vector of length 532 for a given example. So run that, then re-enable these, run this, and now model.fit xtrain ytrain. This is training. Now this is a Keras model, so we can include the extra customization, like batch size and such, but we have to do it in a particular way. Because model is actually a pipeline, if we want to reference arguments for the regressor, we have to do it in this way. We say regressor, because that's what we named it here, double underscore, and then the argument being passed into the regressor. So validation split, 20%. Regressor, double underscore, batch size, 32. Regressor, double underscore, epochs. We'll train for 100 epochs. And then regressor, double underscore, callbacks. And we'll use early stopping callback. So tf.keras.callbacks.early stopping. So we'll monitor the validation loss, set a patience threshold of 3. When the loss stops improving for 3 consecutive epochs, we'll stop the training and restore the best weights. Restore the weights from the best epoch. Alright, and this should work. So let's go and fit that. So I'm not sure how long this will run for. It's not a very good model, if you notice by the loss. Quite a big loss. I really boil that down to the limited data we have here. I don't really see how 3 categorical features and the date can provide an accurate prediction for the funding given to the company. So let's see the results. So we'll just evaluate the model on the test set. Call this results. And also verbose equals 0 so that we don't see the loading bar. And we'll print out the RMSE for the model. So test RMSE. So RMSE is the loss, the square root of the MSE, or the loss. And it's the reason we square root it is so that we get it back in the unit of the original target value. So this is in squared US dollars. When we square root it, we get it back in dollars. So to get results is actually the loss. So I'll just call this MSE because we only returning one value here. We have no metrics. We just have the loss. So the only thing results will get, or the only thing evaluate will return is the loss. So test RMSE, let's display it to 5 decimal places. Actually, since we're doing it in dollars, let's just do it to 2 decimal places. And format this using numpy.square root of MSE. That's the root mean squared error. Then let's just take a look at that. Oh, sorry, it should be score. So we don't need verbose either. Oh, this is actually a bit interesting. Maybe we could do regressor.evaluate. No, it's not going to work. Okay, so what we should do instead is calculate the RMSE ourselves, because the evaluate function isn't available to us since we're using a pipeline. So what we'll do, um, we'll create some predictions. So ypred is going to come from model.predict on xtest, and we'll create the RMSE, and that's going to come from, we take our true values, subtract the predictions. So this is just the error for each example. Then we square the error. So this is the squared error. And we take the mean to get the mean squared error, and then the square root to get the root mean squared error. And then in here we just pass in our MSE. We got an issue. What's wrong here? Let's look at this. We predict on xtest. Oh, this is giving the issue. Oh, okay. So there's actually there's unknown categories. So there's categories in the test set, in the categorical values that aren't in the train set. So we can address this by going into our one-hot encoder and typing in handle unknown equals ignore. This will say if you see an unknown value in a new data set, just ignore it. Don't use it instead of throwing an error. So I'll retrain the model. And then after we get the root mean squared error, I'd like to also get the R squared score. So I imported that at the top. R squared score is basically a measure of how much better your model was doing than the baseline model or the null model. In this case, our y test, these are the prices in our test set. The best thing we can predict without using any of our x's, without any of our features, is to take the mean, predict the mean every time. So R squared score is saying how much better is our error distribution when we do our model than when we just predict the mean for each example. So let's look at this. Alright, there's our RMSE. So what this is saying is on average, our prediction is off by about $56 million. So that's not so great. I mean, we are dealing with quite large numbers here. As you can see, we're in like, I think the hundreds of millions in some of these examples. But that's not really what we want. You know, we'd like to reduce this. 56 million is quite a large margin to be off by. But let's also get the R squared score. So we'll just use the R2 score function from scikit-learn, pass in ytest and ypred, and it will perform the calculation for us. So that's R2, and we'll print it out. Test R squared score. We'll display this one to 5 decimal places and format with R2. Let me just indent this up so they're nice and matching. Alright, and there you go. So it's saying our model is actually slightly worse than predicting the mean every time. So I'm not surprised. However, I did find that by using a different model, I used a random forest regressor, we actually got an R squared of like 0.6. However, the model is still really bad, even though it's doing better than predicting the mean. Because the loss is just so high, it's still not a great model. So I really do chalk this one up to just the limited set of features that we have, especially after having to drop all of those high cardinality and missing value features. What we're left with just really doesn't have much information in it that would be useful for predicting the funding given to a startup. Alright, but that will sum up today's video, so thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.